Hey, it's Mr. Doro. Today we're going to be talking about properties of acids and bases. You guys come in contact with acids and bases every day, whether you know it or not. Doesn't mean that every day you get your hand burned off by acids or anything like that, but the food that you eat is acidic or basic most of the time. The cleaners that you might use in your house are acidic and basic, and acids and bases have lots of properties that we can distinguish just by looking at them or using our senses. So we're going to start with some properties of acids, and I've got 5 of them listed here. And the first one is a sour taste. There are several acids that you can taste, and there are some strong acids that are concentrated that you wouldn't want to taste. But if you were able to taste them, then they would have a sour taste. And I've got a picture up here of some Sour Patch Kids, and I've got this kid that just had a bite of lemon there, and you can see the sour look he has on his face. A lot of our citrus fruits have acids in them, and they could have that sour taste also, and so they have several acids in them. They turn litmus paper red. This is litmus paper right here. Litmus paper is a vegetable dye, and that's why it is that blue color. And then so when you touch it with an acid, it will turn it red, and that's an easy test that we could do for acids. They destroy the properties of bases. What that means is they will react with bases to break them down and to take away their basic properties. That's a process called neutralization, and that is something that we'll be talking about later on also. They will conduct electric current, and we know from last unit that conducting electric current is based on the charged particles that are in the solutions. And so here's a picture of 2 lemons that are hooked up to this little stopwatch, and they're just hooked up through there, and the charges are allowed to pass through because of the charged particles that are in the acids. And something unique to acids is that they react with active metals to produce hydrogen gas. You might remember when we did our demonstrations, we put zinc, it was the bubble pop pop. We put zinc and hydrochloric acid, and it started to bubble as it went up there, and then the gas that was being given off, we put a match to it and it went pop. That was because of the hydrogen gas that was coming off there. So there are some metals that acids will react with to break down and produce hydrogen gas. Make sure that you have all these in your notes. These are things that you need to know about acids. Now here are some base properties. Bases taste bitter, and you can see I've got a couple pictures up here. I've got this lady who's taking some medicine. Cough syrups have base in them as their active ingredient, so that makes them have a bitter taste. And you may remember the song, "A spoonful of sugar helps the medicine go down." That was to offset the bitter taste, and now you see a lot of them have great grape taste or a great cherry taste, something like that, in order to help that bitter taste go down. This is dark chocolate. Dark chocolate can taste bitter also. I happen to love dark chocolate. It actually is pretty healthy for you too. And so dark chocolate, though, the darker you get it, the more bitter it gets, and that's because the more basic it gets. They turn litmus paper blue. This is litmus paper that has been turned a different color because it's normally blue, but turned reddish by an acid, and you put it in the base and it will turn blue. So a way I remember this also is base starts with B, base, bitter, blue. You got 3 B's right there, base, bitter, blue. They do destroy the properties of acids when they're added to acids. That's called neutralization, just like the acids do to the bases. They conduct an electric current also because they produce those charges in aqueous solution, which will allow the current to pass through it. And something unique to bases is that they feel slippery. And so I've got a picture of soap right here. We know that soap is slippery, and that's because they're dissolving the fatty acids and oils from your skin, and then it cuts down on the friction between your fingers as you rub them together. So really, pure soap can be very harsh on people, so sometimes people with sensitive skin, they are actually using a non-soap based product, and so you may not even be using soap when you think you are. What we've talked about so far are physical properties of acids and bases. We haven't even got into the chemical properties of them. And so in about the late 1800s, there were some ideas published about the chemical properties of them, and that's what we're going to talk about now. So in the late 1800s, a Swedish chemist named Svante Arrhenius came up with an idea about what acids and bases do when they're put in water. And he said an Arrhenius acid is a chemical compound that increases the concentration of hydrogen ions in water. So really what that means is this. You have an acid and it would have a hydrogen at the beginning, and I'm just going to put HA for a generic term for an acid. He said that if you put it in water, then what's going to happen is it is going to dissociate or ionize or break apart to make hydrogen ions, that's the hydrogen ions, and an anion in water. And so as you put those in there, it's going to increase the amount of hydrogen ions that are in water. Now, a little bit later on, they found out that, well, these bare hydrogen ions, just a proton, they don't last very long. So a better way of representing this, they said, was this. HA, again, the generic term, put into water, H2O, produces, now see what's going to happen here, is this hydrogen and the anion right here are going to dissociate, break apart, and the hydrogen is going to go over here and join up with the water, leaving this anion all by itself. And so we have H3O plus and the anion over here, whatever that is. Now, this H3O plus right here is called the hydronium ion. And so you probably want to know that this is called hydronium ion, and this one right here is called hydrogen ion, also called just a proton. And the reason it's called just a proton is because hydrogen normally has one proton, one electron. This one has lost its electron, so it's just one single proton, no neutrons. So you'll hear me say every once in a while hydrogen ion or proton or hydronium ion. When I'm saying those three, they're really synonymous with each other, and although they don't technically mean the same thing, they are. That's what I'm meaning. I'll intermix those as I'm going through there. So that is what acid is going to do according to Arrhenius. It's going to increase the amount of hydrogen ions or hydronium ions that are in the water. Now, an Arrhenius base is a substance that increases the concentration of hydroxide ions in water. And so we can draw this out right here, and we're going to draw X. X just means any metal that we have along with an hydroxide ion, XOH, and we put that in water. And that is going to make, it's going to dissociate also. It's going to make the metal ion, that's the cation, and hydroxide ions, OH minus. These are your hydroxide ions. And so when you put these in water, you're increasing the amount of hydroxide ions, and that's what makes it a base according to Arrhenius. Now, Arrhenius did all this work and came up with all these ideas and pretty much wrote a paper on it and presented it, and they gave him a D pretty much on the paper. So it wasn't until later on that they realized that this worked pretty well for a lot of things. It did have to get changed a little bit for the idea of acids and bases because it didn't work in all situations. But just so you know, if you get a bad grade on something, don't give up. Keep on going. Maybe you'll even have your name, like Arrhenius, put on the front of something later on. There are a group of acids called strong acids. Strong acids are an acid that will completely ionize in water. That means you put any of these 7 compounds into water, and they're totally going to break apart. If you put 1,000 of them in there, then almost all of the 1,000 molecules will break apart to make hydrogen ions and whatever the anion is. You're going to have to memorize these formulas and the names of these acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric, perchloric acid, chloric acid, and sulfuric acid. Sometimes these are easier to memorize the formulas if you get a little help. If you look on the back of your periodic table, you have the nitrate ion. The nitrate ion is NO3 with a -1 charge. So since it has a -1 charge, it needs 1 proton or 1 hydrogen ion in order to cancel out that charge. Same thing with perchlorate ion and chlorate ion. But the sulfate ion is a SO4 with a -2 charge, and so it's going to need 2 protons on it to cancel out, or 2 positive charges. Notice that these first 6 that are listed here are monoprotic acids, which means that they have 1 proton each that is ionizable. It's called an ionizable proton. Sulfuric acid is a diprotic acid, which means that it has two protons that are ionizable, which means that they can break off there in order to make hydrogen ions in water. Write down these compounds and their names. Make flashcards if you need to, because you got to memorize them. And here are those words monoprotic and diprotic, in case you wanted to write those down. There are also weak acids. Weak acids dissociate very little in water, so they do have an ionizable hydrogen or more than one. This is diprotic, this is triprotic right here, and this is monoprotic. And this is the only ionizable hydrogen on acetic acid. But when you put them in water, very few of them will dissociate. Most of them are going to stay together, and a few of them will dissociate to make the hydrogen ions in the water. Here's just a list of some that we'll see every once in a while: carbonic acid, acetic acid, and phosphoric acid. They're very common, and they're ones that you should recognize. Strong bases are like strong acids in that they completely dissociate or ionize in water. There's a list of strong bases, and you can figure it out from your periodic table. It is the group 1 and group 2 metals that have hydroxide on them. The only exception is beryllium and magnesium. They're in group 2, and they could have hydroxide, but they would be weak bases. So I've written a couple examples here. You got to watch it when you're writing the formulas, because we have to remember to check the charges. Potassium is a group 1 metal with the hydroxide. You put them together, the charges cancel out, and so you just write it as KOH, potassium hydroxide, and that would completely dissociate in water. Calcium hydroxide is a little bit different though. Calcium is a group 2 metal, which makes a positive 2 charge, and it does not cancel out with the negative 1 on the hydroxide. So you have to crisscross applesauce to make CaOH2 and take the OH 2 times there to cancel it out. Weak bases are not very soluble in water, and therefore they don't ionize much, so they don't make many hydroxide ions, just like the weak acids did for the hydrogen ions or the hydronium ions. Any metal plus an OH besides the strong bases we're going to consider to be a weak base. So, for example, we could have iron oxide, iron 3 oxide, which would be FeOH3. This is a metal with hydroxide joined to it, but it is now our group 1 or group 2, and so that would be a weak base. Also, remember that we had magnesium hydroxide, checking the charges there, makes me crisscross down the 2. Magnesium hydroxide is also a weak base because it's one of our exceptions in group 2. So here's a list of materials that I want you to tell whether it's an acid or a base, and then once you tell whether it's acid or base, say whether it's strong or weak. Remember, if it's an acid, it's going to have an ionizable hydrogen, and usually that's written on the front, and if it's a base, it's going to have a hydroxide group on it that will be ionizable, and then you look at your criteria for strong or weak. Have a nice day.